Hello, I'd like to talk about Quaternion today. So it's a Quaternion. Okay, let me use another color. Quaternion. So that's a very good video on visualizing Quaternion rotation. Online, I will put up the link there, but I want to fill in the gap here, so I'm focusing on unit quaternion. I guess before I get any detail, I guess I need to define quaternion first. So quaternion is basically extension of complex number. You can think of it that way. So if you think of complex number, let's say a plus ib, let's say. So I here is an imaginary number, right? So basically I have I multiplied by I, or I squared is equal to -1. So we say it's imaginary. You know that any real numbers cannot have the square of that is equal to -1. And so if you and then like basically quaternion, when I say it's an extension of the complex number, is that you have not just one type of imaginary numbers. I here I have 3 different types there. So I can have like a plus bi plus cj plus dk, and I have all of these imaginary numbers will, when I square that, will be equal to -1. And what's interesting is that like when I have cost term, of course, like for example I multiplied by j and j minus multiplied by k and so on, I will get something similar to cost product in 3 dimensions. So therefore, like this is like very much related to 3-dimensional space. What I mean is that like if I have mine multiplied by j is equal to k, and j multiplied by k is equal to I, and k multiplied by I is equal to j. And note that this multiplication here is not commute. Basically, if I swap the order here, I don't have the same result. Basically, if I have j multiplied by I have minus k instead, and k multiplied by j is equal to minus I, and I multiplied by k is equal to minus j. And of course, I can also have product of this imaginary part with the real part. So I can have like 1 times I is basically just I. So if I multiply by a real number, real 1 here is just equal to I. Or like if I ai, a times I will be just equal to ai, stuff like that. And this define all basically the multiplication rule. And for the addition will be just simple. If I have a plus bi plus cj plus dk, and this is one quaternion, let's say call this q1, add another quaternion q2, let's say a pi plus b pi I plus c pi j plus d pi k, then will be just equal to a plus a pi plus b pi I plus c pi j plus d pi k, and so on. So it is a very natural definition. And with that, like, we can show that normal curve, this associative law will curve true, that you can't expect that, for example, if I have maybe I, or maybe I just say like if I have like q1 multiplied by a plus b, q1 is something, for example, like that, bi plus cj plus dk, it is actually, I'm not sure I should say define it. It will be the same as q1 times a plus I cannot write it, q1 times bi plus q1 times cj plus q1 times dk. And q1 times bib is like just a real number. You can scale, like put it out. So it's like this is equal to or like q1 times a times b times q1I, and so on and so forth. C times q1j times d times q1k and so let's say this is Q2 here, and this will be the same result if I multiply like Q2 to each of the order first and then I expand it. It will be same result. It's very easy to verify that. So what I mean is my Q1 here, let's say, is equal to this guy here. Here, like, or maybe my Q2 I just give a pi here, let's say. A pi, B pi, C pi, D pi, A pi, B pi, C pi, D pi. So my Q1, let's say, is equal to this guy here. What do I get? I have like A pi plus A pi bi plus A pi cj. So this A pi is multiplied by each of the terms here, and plus A pi c dk, and then I have b pi. B pi is just a constant, I don't care. Q1 times I have to be really careful, like, because Q1 times I is different from like I times Q1. So Q1 times I, Q1 is like what? A plus bi plus cj plus dk times I. This give me like ai plus I times I is equal to minus b, minus 1, so bi times I is equal to minus b. Cj times I is equal to minus ck, and dk times I is equal to dj, and so on and so forth. You can expand that. So actually, if I expand all the terms, if maybe I go back to here, so let's consider this like simple multiplication of this Q1 multiplied by Q2. Let me just write it here. So this is Q1, and Q2 is A pi plus B pi I plus C pi j plus D pi k. And when I have to be careful. This is like this guy multiplied by with this guy, so the order matters. So what you can see is like think of like I'm trying expanding all the terms here. Like I have first like this A multiply. Let's count the real terms here. What will contribute real terms? A times A pi will have real terms here, right? And then like because I need to keep that I times I square, j square, k square, they are all equal to -1. So this multiply this together is all give me -1. I times I will get -1. So I have like b pi here, minus c pi here, minus d pi here. Okay, now let's think of like when I will get I terms here. That is I will get terms I here for the cross term like a times b pi I, right? So I have a b pi here, and also like a pi times b I will get like I here. Now what else will give me I here? If I have like j times k will give me I, right? So cj times dk here will give me I, so I have like c d pi here, and I need to be careful here. This is dk times c pi j. This should give me minus I here, so I have like minus c pi d, something like that. Now what I can finish the whole thing here. So for j will be something like, I can do the same thing also, like what will contribute a j term here. Of course, like a times c pi will give me a j, so I have a c pi here, and then a pi c also give me a j here. Then the cross term between I and k will give me a j. So more precisely, k times I will give me a positive j, so I have like plus d b pi minus b d pi. Oh, by the way, like this ijk here, like I times j equal to k, k times I equal to j, and j to j times k equal to I. So basically, like if you are in the right order, that like ijk, and so on. If you are in the order like ij and then jk and then ki, it will give you positive number, positive positive imaginary number. If you have like swap the order, like j times I, j times I, k times j, I times k, then I will have like negative instead. So if I have like j times I in this order, then I will have like minus k times j in this order, then I will have minus I, and I times k in this order, I will have minus j. So okay, and let's get back to this example here. Then I have also the lastly group all the k terms here will be, I will get k if I have a multiplied by d pi here, and also like a pi times d here, plus I have b times c pi minus b pi times c. So what's interesting is, okay, maybe I look at the real terms here. The real part, if you look at that, if we think of like B, C, D here is I weighted here instead of like A plus like U, and U is like a kind of vector defined by this ijk here. So what I mean is like this first one, like let's say Q1, if I weight it as like A plus U, and Q2 as like A pi plus V, so where U is like bi plus cj plus dk. You can think of this as like a vector, like b, c, d, a vector, like with like different components like I, j, and k. And then like v is something like b pi I, c pi j plus d pi k. And then you look at like b pi, c pi, and d pi. This is really just an inner product between these two vectors, right? So u, if I look at the dot product between these two, is just like b pi plus c pi plus d pi. So therefore, in the sense the real part, I can also write it as like, if I say this is u here, this is v here, then the real part is really a pi minus uv here. And by the way, the imaginary part here, it turns out it's just the cross product actually. If you look at that, if I have vector here, say let me just erase here, I have some space. So if my, again, u is like this guy here, and v is like this guy here, we call that like what's cross product is like. If I have a cross product u cross with v, if you remember, like the easiest way to write it is using a kind of determinant form. Now you can put I, j, k here, and this is like b, c, d. This is b, c, d is the u for the coefficient of u, and this b pi, c pi, d pi, and this will give you the cross product. And the I components is basically what c, d. Oh wait a sec, actually yes, this gives me the cross product here. So I have like c d pi minus c pi d, right? So therefore, like, okay, this part here I have also a b pi plus a pi bi plus a c pi plus a pi c j plus a d pi plus a pi dk. But the remaining part here, as you can verify, is actually really just a cross product, like plus u u cross with v. something like that. So I guess so much for the addition and multiplication of quaternion. And so now let's look at how it's related to the three-dimensional space. Actually, we can map any three-dimensional points. Of course, as you can see, a quaternion is a four-dimensional way. So what I claim is like if I only consider the unique quaternion, basically like if I consider all the a square, all the quaternions such that like the coefficient is normalized to 1, so a squared plus b squared plus c squared plus d squared equal to 1. All this quaternion will map to a three-dimensional matrix point in the three-dimensional space. So M is for a stereographic projection. So namely, so it's something like that. Like in 2D, if I use a 2D example, a stereographic projection to the compass number with unit compass number. So basically on this circle here to the imaginary line. The imaginary line basically is is all the real numbers, right? So I can project any points on this circle on this line by connecting any points here. Let's say if I have a point here on the circle, and this like this -1 and 0 point here, and if I connect them, and then when it project to the imaginary axis here, then each of the point on this circle will be one-to-one project to this imaginary lines here. So for example, if I have another point, let's say here, then it will project to a point here. So just now, if I have a point here, so I have here project to here. If I have a point here, it project to here. So if I give another point, let's say here, then it will kind of like project to somewhere here. And this is like for real for compass number. So we say I only have the regular compass number with only one type of imaginary part. So let's say for the quaternion here, I have 3 imaginary parts. Actually, if I think of 2D first, I mean one-dimensional first, be something like I can map from a ball in 3-dimensional space, a unit sphere, and in a kind of okay, here like I will have 2 imaginary numbers in this 3-dimensional space. 3 imaginary axes. I can have I and j here. So any point on this 3-dimensional sphere will be mapped. Again, I have a point here, say -1. Now I have like 2 imaginary axes. I have 1, 0, 0. So any point on this sphere will be, if I connect, let's say from this -1, 0, 0, if I have a point somewhere here, if I connect a line from this -1, 0, 0 and going through this point, it will intersect with the imaginary plane here and to a point somewhere here. So therefore, like any point on this unit sphere will project to a 2-dimensional plane here, basically the real plane here, or to this space. So for the quaternion, it's just like I have one more dimension. In this case, it's really impossible for me to draw. So I will try to basically have a 4-dimensional ball, like Euler sphere, 4-dimensional ball, and I am going to project any point on the surface of this 4-dimensional ball to a 3-dimensional space. So it's kind of abstract, but like it's easy to find this projection. So let me just derive that because it's quite simple, and but at the same time, I don't think like I see any video online talk about this. So maybe it's good to go through that. So let's say, so what we want is that now we have again quaternion, more precisely unit quaternion, that I have like a plus bi plus cj plus dk is a quaternion, but at the same time like it's normalized, so I have a squared plus b squared plus c squared plus d squared is equal to 1. As I said, like this is like a 4-dimensional ball, surface of a 4-dimensional ball with the centers at the origin, and I want to project this point to the imaginary space. So and the point, okay, if I try to project the point at the line should also intersect with the point in the lower dimension is one lower dimension is like -1 0 0, and in this example, in this 4D dimension, so my line should intersect with like -1 0 0 0, something like that. And also like I want to see like the line there, like I want to see the line that project kind of intersect with the imaginary plane. Actually, in this case, a 3-dimensional imaginary plane. So so first write down the line equation here. The line equation will be something like that. If I consider a line, the direction of the line will go through this point and this point here, right? So therefore, like the direction is something like a minus 1 b c d, right? So this is like, if I write it, of course I can write ijk, so this is more like a vector form here, and let's say I say like parameterized by some s here. This is the direction, so it's like if I increase this s, it will be a longer line, and of course like this line should pass through this point here, so therefore I should add this like -1 0 0 0, right? So this is basically the line equation. If I vary s here, so for example when s is equal to 0, I'll just hit this point here, right? And if I set s is equal to, let's see, when s is equal to 1, yes, s equal to 0, I will get this point here. When s is equal to 1, then basically I will get to this point here, right? So this is like q0, q1, let's say. So when s equal to 0, I will get back q0, and s equal to 1, I will get back q1. So that's what I want. Now what I'm interested in is like when it intersects at the imaginary plane, right? So when I intersect at the imaginary plane, it means that the real component here is equal to 0. I can write this whole thing here, like it's equal to, now it's actually equal to a plus 1s minus 1 b c d, right? Now I want to see this line again, like this line intersect with the imaginary plane. So that means the first component, the real component, should be equal to 0. So I want SA plus 1 is equal to 1. That's all. So, and when that happens, basically this coordinate here will give me the coordinate, the 3D coordinates. So therefore, like I basically have, in this case, this will give me what s equal to 1 over a plus 1, right? And wait, I'm sorry, like I should have s multiplied to here also. S multiplied by b, and s multiplied by c, and s multiplied by d here. And so therefore, like when s equal to s equal to 1 over a plus 1, I have basically 0, sb, sc, sd, or like 0, b over a plus 1, c over a plus 1, and d over a plus 1. And this are the 3D coordinates x, y, z here. So that means that like if I have a quaternion, a unique quaternion A, B, C, D, after stereographic projection, it's actually projecting to a point in a three-dimensional space. The point is actually at like, so what I mean is that x, y, z is actually equal to b over a plus 1, c over a plus 1, and d over a plus 1, something like that. That's the projection. And we can go the other way around, right? So this is the projection for from, let's say, a quaternion or unique quaternion into the three-dimensional points. Now if I want to get the representation, let's say if I have a three-dimensional points here, like my three-dimensional points x, y, z. So what was my like quaternion? So this will be just getting reversed, right? So it's a little bit more algebra, but like as you can see here, like if I have x, y, z here, I should have like my quaternion should satisfy this, like x is equal to b over a plus 1, and so on and so forth. And remember that my a plus 1 is actually equal to actually erased that already, but let's see if I can go back not to erase all everything actually. Yeah. Or is it too far actually? Okay, it's here, it's back here. So I have yeah, I have x, y, z. If I go back to here, I can also write like x, y, z as like s a, s b, s c. Oh sorry, s b, s c, s d. S b, s c, s d, where s is equal to 1 over a plus 1. So now let's see. So then if I consider, let's say, a squared plus b squared plus c squared plus d squared, so we know this will be normalized to 1. But b squared is equal to, let's see, b is equal to x over s, right? And c over equal to y over s, and so on, d equal to c over s. So I have like this is actually x squared plus y squared plus c squared over s squared. And maybe I can call x squared plus y squared plus c squared, just call it r squared. So it's like the radius, or like the length, the distance from the origin. So let's say this is equal to a squared r squared over s squared, something like that. This should be equal to 1. So therefore I have let's see, I can just move the terms around. So I have like r squared over s squared equal 1 over a squared, or s squared is equal to r squared over 1 over a squared, something like that. Now I remember also s is equal to 1 over 1 plus a. So therefore, like, what do I can substitute one of the s on this side here. So I have s 1 times 1 over 1 plus a is equal to r squared over 1 over a squared. So then 1 minus a squared is equal to 1 plus a times 1 minus a. So I get one of these got cancelled. So therefore is s is equal to r squared over 1 minus a. So then I will have two equations, basically s equal to 1 over 1 plus a, and also s is equal to r squared over 1 minus a. So use these two equations. I guess I don't need this anymore. So this time I can really erase this. So I have like s plus sa equal to 1, and also s minus sa equal to r squared. I just multiply this 1 over a and 1 minus a to the other side. So then I want to solve for I want to solve for what? I want to solve for s, right? Let's see. Then I add them together. Then this sa got cancelled. Then 2s is equal to 1 plus r squared. I'm done. S equal to 1 plus r squared over 2. So therefore, if s is equal to this guy, and then I know s also equal to 1 over 1 plus a. So therefore, like 1 plus a is equal to 1 over s, or a is equal to 1 over s minus 1. So and this gives me basically a is actually it's okay. I can stop here. I think I'm happy with that. So s is equal to this one here. A is equal to 1 over s minus 1, or I can make 1 minus s over s. And remember that like B, C, D is actually just equal to x, y, z over s here, something like that. So I can put everything together. It's like I will have from 3D to Quaternion. So it's basically if I have x, y, z here, if I write it a Quaternion from like my a, b, c, d, maybe something like 1 over s, 1 minus s, x, y, z, something like that. And also s is equal to this 1 plus r squared over 2. So this is like, we have basically a mapping of all the unique Quaternion. That's basically a plus bi plus cj plus dk, such that like a squared plus b squared plus c squared plus d squared is equal to 1. For that to map to a point in the 3D space, so in that case, like x, y, z is just equal to b over a plus 1, c over a plus 1, and d over a plus 1. Or we can have the point in the 3D space, x, y, z, map it back to a Quaternion as like a, b, c, d. Each of that's coefficient will be just equal to 1 over s times 1 minus s, x, y, and z, where s is just 1 plus r squared over 2.